Okay, let me remind you of something. So this is going way back to one of the first lectures of the whole course. So remember this thing about lattice paths? So how many lattice paths are there from 0, 0 to n? Where in a lattice path, remember what you do, you start at 0, 0, right? You start at the origin, and the kind of allowed moves that you can do is you can take one step to the right or one step up. Oh, sorry, I got this all messed up. So if I take a step to the right, I go to 1, 0, right? Or you can take a step up and go to 0, 1, right? And you kind of take steps to the right or up and try to reach n. And so yeah, I recognize that this was a long time ago, but yeah, this is a bit of review, I guess, right? And the idea for how to solve this was like, you know that if I go from 0, 0 to n, I have to take 2n steps, right? And n of them have to be up steps. And so basically taking a lattice path from 0, 0 to n is the same as saying I'm going to do 2n things, either up or right, and I want to choose n of them to be up. So yeah, the answer is 2n choose n. So what we're going to do is look at a variation of this question. So we're going to look at lattice paths that have a certain type of restriction, and we're going to use recurrence relations and generating functions to count the number of lattice paths with a certain restriction. So here's the restriction. So the question we're going to address is how many lattice paths are there from 0, 0 to n which never go above the line y equals x. So the kind of picture is like this. I've got 0, 0, I've got n, and you've got some kind of, you imagine you're kind of on a grid, right? Every step, so this is supposed to be a square. It obviously looks very rectangle, but oh well. And what the restriction says is that you're not allowed to cross this line. So obviously you can be on this line because 0, 0 is on the line, and so is n. But basically the path has to go, maybe it does something like this, and it stays below the line the whole way. Is it clear from the picture? So what's forbidden? So it's forbidden to like do something, go up, and then go across this line. So is the question clear? So in other words, the restriction is that if you have some ij that's on the path, then like every ij on the path must satisfy that j is less than or equal to I. Like the y coordinate has to be less than or equal to the x coordinate. And this is more complicated because I can't just take my 2n steps and choose some of them to be up. There's a certain restriction, right? I can't have, suppose I start with going right 3 times, let's say. So I start at 0, 0, I go right 3 times. After I go right 3 times, I can't go up 4 times, right, in a row. So that's like a kind of a weird restriction, which is kind of hard to capture, right? If I go right once and right again and then up and then right, then I'm not allowed to go, so I've gone right 3 times, I've gone up once. I'm not allowed to do 3 ups in a row, for example, right? These are things that are not allowed because you would go above the y equals x line. Okay, so let's count this for a few small values. So what about the case n equals 1? Well, I guess I can do that myself. So how many ways can I go from 0, 0 to 1, 1 without going across this line? Well, all I have to do is, I have to go right first, because if I go up, that's going to be bad, right? That goes above this line. So for n equals 1, there's just one path. What about n equals 2? So I'll let you guys think about that one. So any thoughts? How many paths are there for n equals 2? Yes, that's right. So I believe there's 2 paths because, if you can, one thing you can do is you can go, right, right, up, up, or you can go right, up, right. And anything else you do is going to be bad. For example, so one observation here, like the first step has to go right. Like there's no choice, right? And that carries on further, because if you take the first step going up, then obviously I've already failed my condition. So kind of the first step has to go right. The second step, you have a choice. It can go up or right. And then based on what you did, the number of choices, it depends on what you choose for the second one. And then it becomes a bit complicated. But definitely your first step has to be right. Okay, so here for n equals 3, suppose I go, one option is I could go right, 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 up, up, up. It's 1, I could go right, up, right, right. I don't know how I really expected you all to be able to count this. I mean, I could go right, right, up, up. It's another one. I guess I could kind of do it based on when's the first time I go right or up or something. I don't know. Go right, up, up. It's another one. It might be 5. I'm willing to kind of believe you. It looks like 5, doesn't it? Because so I've done these 3, and then I could have gone up twice here and then over. So that would be another one. I could have gone up twice here and then over, and that would be another one. And I don't think there is any other apart from that. So I think you're right that it's 5. For n equals 0, I don't remember what I had planned for this. It's either going to be 0 or 1, depending on what's convenient. But we'll think about this maybe later. Okay, so let's try to get a general formula for this using by setting up a recurrence relation and using generating functions to solve it. So I'm going to define Cn. So it looks like I define C0 to be 1. And that makes sense. If I wanted to go from 0, 0 to 0, 0, there's only one way to do it because I just don't do anything. That makes sense. So let's say n equals 0. The answer is 1. Okay, so let's let Cn be the number of ways to do it. So the number of lattice paths which don't cross the line y equals x from 0, 0 to nn. And so like I said, we want to come up with a recurrence for Cn, and then we want to use generating functions to solve it. And we've kind of already answered this question. So if we think about the first step of the path, it has to go right, because if it goes up, then you've already lost. You've already gone above the line. So that's going to be useful in setting up the recurrence. But we need something else. This is a little bit of a trickier one. But think about this. So imagine we follow the path. Of course, at the end, we end at nn, right? So there must exist a time when this path comes back to the y equals x line, because in particular, it comes back to the y equals x line at the end. But instead of looking at the end, let's look at the first time that the path comes back to the line y equals x, okay? So it could be at the very last step, or it could be earlier. We don't know. But imagine the first time it comes back to the line y equals x. And so let's say it comes back at the point I. So the picture looks like this. We've got nn here. We've got 0, 0. And the path does something, blah, 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 blah. And it comes back to the line at the point. Oh, it doesn't do that. Whatever. At the point I. So my question is, so again, on this picture, maybe it looks kind of clear, but in general, like, where was the previous location before it came to I? Meaning, basically, if I look at I and I take a step back, where does it go? Yeah, and it has to be, so there's kind of, in theory, there's 2 options, right? Because if I take a step backwards, that step either goes left or it goes down. So it's kind of like, it could have been here or here. Sorry, I minus 1. But I think probably you're kind of noticing here that this one's impossible. That one's bad because this would have the y coordinate bigger than the x coordinate. So when I look here, if I take a step backwards along my path, that step must go down. It cannot go left because that would be above the line. Is that clear? This just seems like a irrelevant fact at the moment, but that's going to be quite useful for setting up the recurrence. So what we've learned so far is that the first step always goes right, and that if I look at the first time it comes back to the line y equals x, then the step before that always goes up, the previous step. Is that clear? It's kind of weird to think of, because it's a bit abstract maybe to think of the first time it comes back and that sort of thing. But yeah. But by the way, the first time it comes back to the line could have been at nn. So for example, you could take this path, which just goes right, and then up, right? But the thing is, it's still true because the previous thing was here. It was n minus 1. Okay, so what we're going to do is use these observations about these steps of the path to set up a recurrence relation. So here's the idea. So first of all, let's actually look at the second part of the path first in some sense. Like if I look at this from here to here, so if we think about the way to think about recurrence relations is sort of to think kind of inductively. And so what do I have here from II to NN? I've got a path that starts at I. It never crosses the line y equals x, and it goes up to n. So how many ways can I do that? Oh, I guess maybe I might have the answer here already, but yeah, how many ways can I go from I to n without crossing the line? And really, that's the same as if I shift everything. That's the same as thinking of starting here at 0, 0 and going up to n minus i. So the number of ways to do this part of the path is going to be c n minus i. Just c n minus i. Is that part clear? Because really, this can be thought of as a path from the origin to n minus i. The more kind of, but well, actually, maybe first of all, so is that part clear? The fact that this one is just a, the number of ways to go from here to here is just this, just kind of, so remember Cn is the paths from 0, 0 to nn, right? And if I go from I to nn, it's the same as going from 0, 0 to n minus i. So C sub n minus I counts the number of ways to do this part of the path. Now, how many ways can I do this part of the path from 0, 0 up to I? And it's tempting to write Ci because it feels like that's the right thing to write because it's a path from 0, 0 to I. But there's something special here so you have to take advantage of the fact that this was the first time we returned to the line y equals x. And since this is the first time, so I is the smallest, the first time we return to the line, we know that actually none of these points in the middle can be on the line. They all have to be below the line, like strictly below the line. Okay, which, I mean, if you look at the picture, it's kind of a tricky thing to visualize maybe, but what this really means is that, so remember, we know that the first step goes to the right, and we know this step goes up, right? If I kind of imagine I remove those two steps, then I look at this green path, and I kind of think of it as the origin being here. Then this green path actually looks like a path from 1, 0 to I minus 1 that doesn't go across this purple line. Because if it goes across the purple line, then that would be another point that is on the line y equals x that comes before this one, and that would be a contradiction. And now how many paths go from 1, 0 to I minus 1 without crossing this line? So this is the line y equals x minus 1. And if you think of kind of shifting this to the left, this whole thing to the left, you can see it's the same as paths that go from, the number of paths that go from 0, 0 to I minus 1 that don't cross y equals x. So that's kind of doing a transformation where we kind of subtract 1 from the x coordinate here, subtract 1 from the x coordinate, and kind of shift the picture to the left. And yeah, I'm not sure if this is clear or not. I think it's a little bit tricky to see this, but are there any questions about this? Do you see what's going on here? So the number of ways to go from 0, 0 to I without touching so basically what I'm saying is the number of ways to go from 0, 0 to I without touching the line y equals x, except at 0, 0 and I, is equal to Ci minus 1. Because it's the number of ways to take a step to the right, and then to walk to I minus 1 without going above this line, and then taking a step up. But if you don't go above this line, then you could think of shifting the whole picture to the left, and it's the same as going from 0, 0 to I minus 1 without going over the line y equals x. So it takes a little bit to visualize it. But what this gives us is that the number of paths that come to where the first time they reach the line y equals x, or return to that line is at I, is equal to Ci minus 1 times Cn minus I. And so the total number of paths that we're counting, so Cn will be the sum over all I of this value. So what we've derived is that Cn is the sum of I equals 1 up to n. So here, we're thinking of I as being the first time the first time we get back to the line y equals x is at I. The number of paths which have that property is Ci minus 1 times Cn minus I. We sum that up from I equals 1 to n. And we can think of shifting the, indices here. So if I think of I equals 0 or 1 here, that says C0 n minus 1. Then I've got C1 n minus 2, Cn minus 2, right? if I think of starting this sum at 0, then it should be ci c sub n minus I minus 1, because it should start, so this should start at 0 when I put in 1, because this starts at 0. And anyway, so you could do this with a little substitution if you wanted, like j equals I minus 1, and then, yeah. So this is a recurrence relation. This is not the type of recurrence relation we're used to, because usually when we see a recurrence relation, it looks like, I don't know, Cn is 7 Cn minus 1 plus 3 Cn minus 2 or something, plus 2 to the n, okay? This is the type of thing we're used to. This is not that, because here I've got my previous, so Cn is some function of the previous Ci's, but they're being like multiplied to each other in a weird way. So it's not the, yeah, it's not the same thing. Okay, but it is a recurrence relation. It's just a non-linear recurrence relation, because you have the Ci's being multiplied to each other, the previous terms being multiplied to each other. So let's see how to solve this. By the way, I wanted to kind of, maybe I should mention, this type of formula, or this type of sum, you might have forgotten, you know, ever seeing something like this before, but you have seen things like this before. Remember, if I have, there was this thing about products of generating functions. So remember, if I have, let's say I have f of x is the sum n equals 0 to infinity an x to the n, and I have g of x is the sum n equals 0 to infinity bn x to the n. And I know this was a long time ago, but we've talked about this a few times. If I take the product of two generating functions, then if in this product, the coefficient of x to the n is going to be the sum of I equals 0 up to n, an b n minus I. So we've talked about this before. And this thing, okay, it's not quite the same because I've got an n minus 1 here and an n minus 1 down there. But can you see how it's kind of the same? Like, except that these are both c's and whatever. It's kind of the same as this, right? And this kind of suggests to us that a natural thing to look at, so if I let f of x be my generating function for the c's, then it might be natural to look at f of x times itself. Because if I look at f of x times itself, I'm going to see coefficients that look like this, except maybe slightly shifted or something like that. So when you see things like this, you should think, oh, I should look at a product of two generating functions, because that's going to have the right type of coefficients. Okay, let's look at, so yeah, here's a, maybe now that I've explained that intuition, maybe it's not that weird of an idea. But yeah, so if I let f of x be the generating function for Cn, what we might want to do is look at the square of f of x. So what is the coefficient of x to the n in f of x squared? Well, it's going to be the sum I equals 0 up to n ci times cn minus I, which is, like I said, almost the same as our recurrence relation for Cn, but not quite. So is it clear how I got this? So this is just, I'm just defining f of x like this, and this is a standard thing. If I take f of x squared, the coefficient of x to the n is just like you, yeah, you do this kind of, it's basically like saying, how can I get an x to the n from this times itself? Well, I can take the x to the 0 times the x to the n, or the x to the 1 times the x to the n minus 1 thing. And if you add up all of these different choices of coefficients, it gives you this. So this is what I said, that this is equal to this, except I put I instead of k, but it's the same thing. And actually by a recurrence relation, remember we wrote down this recurrence relation for Cn. If you plug in n plus 1 into that, this is actually just Cn plus 1, because we said Cn is like this. So Cn plus 1 would just be the same thing, except put a n plus 1 in for n. And this is true for all n at least 0, because our previous thing was true for all n at least 1. And if n is at least 0, then Cn plus 1, or n plus 1 is at least 1. Okay, so here's what we've said. F of x is this, okay? F of x is just the sum n equals 0 to infinity Cn x to the n. That's just by definition. And what we've observed through this, through the recurrence and properties of generating functions, is that f of x squared is the sum from n equals 0 to infinity, Cn plus 1 x to the n, which is like almost the same thing as this, right? It's just there's an n plus 1. But this gives us a way to come up with an equation, right? If I take my f of x squared, I times it by x, that's going to add 1 to all of these exponents, right? So that's the sum n equals 0 to infinity, Cn plus 1 x to the n plus 1. Then I can do my usual index shifting whatever, because this really, if n is 0, these are both 1, so I can really just start this at 1 and go n equals 1 to infinity and write Cn instead of Cn plus 1 x to the n. And now this really is pretty much f, right? If I compare these two things, all that's missing is the 0 term, and the 0 term is c0 x to the 0, which is 1. So what I can conclude from this is that f of x is 1 plus x times f of x squared. Now, here's a question to you. So, okay, I can also put everything on one side. So that's what I'm doing here. I'm just moving the f of x to the other side. Here's a question to you. How do you suggest that I come up with a formula for f of x? So what should I, so this is my equation. I'm wondering, what is f of x? Like, what should I do to find it, to find f of x from that equation? Any thoughts? This is a weird looking equation, right? But if I told you that, if I told you this is xf, that this is true, that this equals 0, any thoughts about how to solve for f of x? Something like that. It's very related to this whole characteristic equation stuff. Yeah, these are all good ideas, but you actually know something which is much simpler. Actually, it's kind of related to this characteristic equation thing, but well, the characteristic equation is usually if you have a recurrence relation, then you, kind of factor. So all I'll do is just use so it's hard to factor this because there's this weird x and f. But if you think of f of x as being y, let's say, okay, xy squared minus y plus 1 equals 0. Now I want to figure out what y is. The annoying thing is I have this x here, so that kind of, but I can do that because I know the binomial, or what do you call it? The quadratic formula. This is just a quadratic involving y. So I can just plug it into the quadratic formula. It's just that this will, like this negative b plus minus a squared, or b squared, whatever that thing is. It's just that my a in the quadratic formula is an x, but I can still use it, right? So I can just use the quadratic formula for this. And so what the quadratic formula says, if I apply it with this equation, right? So my b is negative 1, so I get a 1 here. I have my usual plus minus thingy. I have square root of b squared minus 4ac, c is 1, a is x, which is weird, but I can do it, right? I could just plug it in. And then divided by 2a, where again, x is equal to, or a is equal to x, so it's over 2x. Okay, is that clear? Now, I wanted to solve for f of x and just have a kind of write out a formula for f of x. The plus minus is very strange because this is kind of like, it says that f of x could be two different things, which seems wrong. And that is sort of wrong, but we're going to work it out later. So later we're going to say, so let's keep the plus minus for now. And then later we'll think about, okay, which one is correct? Like, is it the plus or the minus? And it'll be clear at some point. So we'll keep the plus minus and we'll get rid of it later. Okay, but f of x is this. Well, it's this or this, depending, what the plus or minus is. It could be two different things. Okay, so, right, so I want to find the coefficients of f of x, right? F of x is Cn x to the n, right? Sum overall n equals 0 to infinity. I want to know the coefficient of this. So it's the same as trying to work out the coefficient of the right-hand side, the coefficient of x to the n in the right-hand side. So the kind of most weird part of this is the square root. So what is the coefficient of x to the n in the expansion of this thing? And believe it or not, we've done this. So, right, a square root is just a power of 1/2. So if I write, so what is 1 minus 4x to the half? And this comes down to this whole Newton binomial theorem thing, right? So this is going to be 1/2. Oh, sorry, what am I writing here? 1/2 choose n, right? Where this had a sort of specific definition, which we'll come back to. So Newton's binomial theorem was for like 1 plus x to the p. I've got a minus 4x here. If you do the substitution, you get a minus 4 to the n. x to the n. So the coefficient I'm looking for is this, right? Right. So this is just rewriting what I had on the previous slide up here. Now, the only part of this that I'm not very, like right now, you shouldn't be very comfortable with is the half choose n. Or, I mean, you know how to compute it because we've talked about what this is, but it would be better to kind of understand exactly what this is. So you might remember back when we did this Newton binomial theorem thing, we looked at this. We looked at negative a half choose k, and we came up with a formula for it. And actually on your assignment, you had assignment 4, you had a more complicated version of this that you had to do involving 1/3 and 2/3 or something. And if you follow that same kind of approach, you can also determine 1/2 choose k for each k. So I'll maybe skip those steps because it's something we've seen before now a couple of times. So it's the same kind of idea as how you prove this. And it turns out 1/2 choose k is just -1 to the k minus 1 over k times 2k minus 2 choose k minus 1 divided by 2 to the power 2k minus 1. And again, you can prove this. So if you just follow the same argument as for this one, and you just kind of think of a half instead of negative a half and see what would change, then it should work out. Okay, so this is good news. So this is going to help us compute our f of x, or the coefficients of f of x. So this is what we wrote before, that f of x is equal to this stupid plus minus thing. So 1 plus minus the square root over 2x. Let's take out the 2x, okay? Then we just get 1 plus or minus the sum n equals 0 to infinity of -4 to the n. So I'm just writing out this square root thing again, a half choose n x to the n, and we've worked out what a half choose n is. So we can substitute in that formula. So from this line to this line, all I'm doing is substituting the formula from this slide here, this one. And now we can see that there's some cancellation because I've got this -1 to the n, and here I've got -1 to the n minus 1. So that becomes like -1 to the 2n minus 1. 2n minus 1 is an odd number, right? Because it's 1 less than an even number. So if I take -1 to the 2n minus 1, that's always going to be -1. So here I'm just kind of combining this with this. I can also sort of cancel my 4 to the n with most of this, except there's this -1 here. So if I take 4 to the n over 2 to the 2n minus 1, that's equal to 4 to the n over 4 to the n 2 to the minus 1. So I'm just kind of taking out this -1 and noticing that 2 to the 2n is the same as 4 to the n. And so this is just, so if I have 2 to the minus 1 on the bottom, that's just 2, right? Because these cancel. So at the end of the day, I've got this, right? So this is just doing the cancellation and all that, and you get this. So now this is the formula we've come up with. So by the way, so if you are at this point worrying that you will never be able to repeat these steps by yourself, so just a quick thing that like, you're not going to be asked to solve nonlinear recurrence relations. So I'm not giving you a method for solving all of them. But this is kind of more just, I mean, to be honest, I think this is just an interesting example that you should see. But you should be able to, basically, if I told you to do some of these steps, if I gave you the steps and I told you to execute them, you should be able to do it. But you don't necessarily have to be able to remember how to do all these steps. But if I gave you a question that said part A, do this, part B, do that, part C, do that, you should be able to follow those steps if I told you what the steps are. Okay, so what we've come up with so far is that f of x is this. And we've still got this kind of stupid plus minus 1 here. So it's kind of like f of x is one of these two different options with the plus or the minus. So we need to work out whether it's a plus or a minus. Now, one way to work that out is to say that we know that, so f of x is, we define it to be this sum cn x to the n. And in particular, if I take f of 0 should equal c0 because all the other terms disappear. And the thing is, imagine I plug in x equals 0 here. I've got a 1 over 2 times 0, which is bad. You're not supposed to divide by 0. That's bad. And then I've got times like 1 and then this, and then all of this will go to 0 because this is the sum from n equals 1. So this part goes to 0 if I plug in x equals 0. And I kind of need this part, I kind of need this whole thing to be 0 because otherwise I've got this 0 over 0. So in some sense, actually, another way to think of it is that I've got this x on the bottom. Okay, f of x is not supposed to have an x on the bottom. It's supposed to look like this. So I need that x on the bottom to cancel out with another x. And if you think about it, the only way that can work is if this is a negative sign. Because if that's negative, I get 1 minus 1, so those cancel. And then I've got a whole bunch of things that have an x in them, and this one of these x's can cancel with that x. So through this kind of, thinking about what would happen if we had a plus or a minus, you can work out that this actually has to be a minus, because otherwise f of x would not, or f of 0 would be undefined. So it has to be a minus. I know that's maybe not the most satisfying way of answering whether it's a plus or a minus, but that does work. So we assume that this is a minus sign, and so the ones cancel, right? I have a 1 on this side minus a 1 on that side, and also this minus 1 goes in here and it makes that a plus. So at the end of the day, what I've got is that f of x is 1 over 2x times the sum n equals 1 to infinity of 2 over n times this 2n minus 2, choose n minus 1 times x to the n. And now I can bring in this 2x and cancel out some stuff, right? So that'll cancel the 2, and that'll cancel one of the x's. So that becomes an n minus 1. So I have this. Now I do my usual, shift the indices. And so what I get is the sum n equals 0 to infinity of 2n choose n over n plus 1 x to the n. And now at this point, it's easy to remember, it's easy to forget where we even started and what we were even trying to do. But we've succeeded. We've succeeded in our goal. We've determined that this Cn is 2n choose n over n plus 1. So this is equal to the number of lattice paths from 0, 0 to nn that don't cross the line y equals x. So I thought I feel like this is kind of magical how this kind of works out. And this combines a lot of the different things we've done so far. This is an example of a nonlinear recurrence relation. So I understand that was kind of a complicated argument, but are there any questions about that? So like I said, my feeling about this is that the big picture here is too complicated to ask you to do in an assignment or a test, to do the whole big picture. But I feel like lots of these little steps I could ask you to do. Like I could ask you to determine that this formula for 1/2 choose k, for example. Yes. So that's a good question. So for this minus sign, the minus is defined, but the plus is not. So imagine I choose the plus here. So I'll do this in this little box. I'll make a box here. So if we choose the plus, it's the plus, if I choose a plus, that's not defined. Yeah. So if we choose plus, then what it looks like is 1 over 2x. So I have a 1 here, I have a 1 here. So if this is a plus, then I have 2 here, like 1 plus 1 is 2. And then we have this sum n equals 1 to infinity of like the same stuff. It's 2 and whatever. It's actually not going to matter what's here. We're going to have, problems anyway. Now, we know that by the way we defined f of x, remember we defined f of x like this. F of x should satisfy f of 0 equals c0. Like this should, my f of x will satisfy this, because if I plug in x equals 0, you have c0 x to the 0, which is c0. Because all the other terms, anyway, it's kind of, okay, you kind of have 0 to the 0, but we think of that as being 1. C0, so f of 0 is c0. But if f of x is this, then I claim that it's not going to be c0, and it's not even going to be defined. It's going to be, we're going to divide by 0, because if I plug in 0, I get 1 over 2 times 0 times 2 plus, and this thing is 0, because all of them have an x to the n, where n is at least 1, but that's not defined. So in particular, this cannot be f of x, because f of x at 0 should be c0. And here, this choice of f of x is undefined, so it can't be correct. It has to be wrong. So the minus sign has to be right. I know it's kind of a weird argument, but is that better? Does that help? Yeah, so it's just like what happens if I plug in x equals 0. And yeah, you can't divide by 0, right? So if I take 2 over 2 times 0, 2 over 0 is not defined. Oh yeah, if it's minus, here's the thing. So if it's minus, it seems like we're taking 0 over 0, which also looks bad. But the thing about if it's minus, if you plug in the minus, it's a little bit different than this because what happens is the ones cancel, and then you can cancel the x's, okay? So then you don't have 0 over 0 because you cancel the x's. So there's no more x on the bottom. So that's what happens here. So if you plug in the minus, it gives you this. But now what you can do is say, oh, that x cancels with one of these x's because this starts at 1 and goes to infinity. So all of the terms have an x, so I can cancel that x with that x. That goes to n minus 1. And now I don't have any division by 0. It's kind of slick how it works out. It almost feels magical, but it kind of had to work out. Yeah. This is one of the things you have to kind of go away and think about how that worked. But yeah, so this is this is the number of lattice paths that don't cross the line y equals x. And yeah, it kind of has, remember, if you just count all the lattice paths, it's 2n choose n. So it has that in it, right? 2n choose n. But personally, I would have never guessed that it's 2n choose n divided by n plus 1. That's bizarre, but that is the answer. And if you went and checked like some small values like n equals 1 and n equals 2, n equals 3, it's going to match up with what we found before. So I just wanted to mention that this number, 2n choose n over n plus 1, this is actually a famous number in combinatorics. So it's called the nth Catalan number. That's actually why I call it Cn. So if you were wondering why was it C, C stands for Catalan. And so this counts the number of these lattice paths that don't cross the line, y equals x, but it also counts a lot of different things. So there's this book, for example, by Richard Stanley, where he makes a list of 66 different things which are counted by the Catalan numbers. And they all kind of seem different from each other, but they all turn out to be equal to the Catalan number. That's kind of an interesting thing.